Hello, bachcho. Welcome. Today, we're starting a very important and, trust me, a very interesting chapter. Unit 9, Ray Optics and Optical Instruments. I know optics can sometimes feel a bit tricky, right? But I promise you, by the end of this session, the basic ideas will be so simple in your head, you'll remember them for life. And most importantly, we will learn exactly how to write our answers in the exams to get full mark.
Okay, so chalo, let's start with a very simple question. You've all seen this, haven't you? You put a pencil or maybe a straw in a glass of water and it suddenly looks bent. It looks broken right where it enters the water. So what's going on here? Is it some kind of magic trick? Well, no, it's not magic at all. It's pure, simple physics. It's just light playing a few simple tricks on our eyes. You see, the light that's coming from the pencil inside the water travels differently from the light coming from the part that's in the air. And this is the whole mystery we are going to solve today. Now, to understand these tricks of light, we first need to meet the main player of our story, the hero of this entire chapter, the light ray. Believe me, everything in ray optics is based on understanding this one simple idea. So, what is a ray of light? It's really simple. It's just the straight path that light travels along. Just imagine a single, super thin line of light moving in a perfectly straight line. That's one ray. And when you get a whole bunch of these rays together, like the light from a torch, we call that a beam of light. Simple, right? To make it even easier, just think of a fast bowler throwing a cricket ball, but he throws it perfectly straight. No spin, no swing, nothing. The path that ball takes, that dead straight line, that is exactly how you should imagine a light ray. It's a fantastic mental picture, so please keep it in your mind. Okay, so this light ray, it follows some very simple rules. Let's think of it as a game. And rule number 1 is this. When our light ray hits a smooth, shiny surface, like a mirror, it bounces off. This bouncing of light is what we call reflection. Now here is the exact law of reflection. Please note this wording down carefully. This is straight from your NCERT textbook. If you write this exact sentence in your exam, you get full marks. It has 2 simple parts. 1, the angles are equal. And 2, all 3 lines, the incoming ray, the outgoing ray, and the normal, are all on the same flat surface, or what we call a plane. So how does this actually work? Let's break it down into 3 simple steps. First, our light ray, which we call the incident ray, comes in and hits the mirror. Step 2, right at the point where it hits, we have to imagine a line at 90 degrees to the surface. This imaginary line is super important. We call it the normal. And third, the light ray bounces off. This is our reflected ray. The most crucial point here is that the angle at which it comes in, angle I, is exactly equal to the angle at which it goes out, angle R. Always. All right, so light bounces off mirrors. That's rule 1. But what happens when light goes from one transparent thing into another, say from air into water? It doesn't just bounce back, it goes inside, but it bends. This bending of light is our second rule. It's called refraction. And this, bachcho, is the secret behind our bent pencil. Let's go back to our cricket ball. Imagine it's rolling really fast on a smooth green cricket pitch. Now, what happens if it suddenly rolls onto a sandy patch next to the pitch? It will slow down, won't it? And its path will change a little bit. It will sort of swerve. This is exactly what happens to light. Air is like the fast pitch, and water is like the slow sand. When light enters the water, it slows down and it bends. What a perfect way to understand refraction. And just like reflection, refraction also has a very precise law. It's called Snell's law. And for your exams, this formula is everything. It simply says that if you take the sine of the angle of incidence and divide it by the sine of the angle of refraction, you will always get a constant number for those 2 materials. This constant is called the refractive index, and it's the key to solving pretty much all the numerical problems on refraction. So which way does the light bend? There's a very simple rule for this. Just remember, when light goes from a rarer medium, like air, into a denser medium, like water, it slows down, and it bends towards the normal. That path gets a little closer to that imaginary 90-degree line we talked about. Now, attention. Listen up, everyone. This is super important. This is a common trap in exams where so many students make a silly mistake and lose marks. We absolutely have to understand the difference between optical density and mass density. So here's the point you must remember. In optics, when we say a medium is denser, we do not mean it's heavier. Optical density is all about how fast light travels in it. That's it.
Mass density, which you study in chemistry, is about mass per unit volume. They are two totally different things. And the perfect example to remember this is turpentine oil. Light travels slower in turpentine than in water, so we say turpentine is optically denser. But, as we all know, oil floats on water, which means its mass density is less. Remember this example. So now that we know light can bend, what if we could bend it so much that it never escapes from the medium at all? What if it gets trapped inside? Well, this amazing thing can happen, and this phenomenon is called total internal reflection, or TIR.
Now, for this magic to happen, two conditions, two golden rules must be met, no exceptions. First, light has to be going from a denser medium to a rarer one, for example, from water out into the air. And second, the angle at which it hits the surface, the angle of incidence, must be greater than a special angle for that material called the critical angle. If both these things are true, poof, no more refraction. All of the light gets reflected right back inside.
And you know what? This principle of TIR is the reason our internet is so blazing fast. Inside those optical fiber cables, light signals are sent down a super thin glass fiber. They hit the inner walls at an angle greater than the critical angle, and they get totally internally reflected again and again and again, zipping along for kilometers with almost no loss of signal. It's all TIR in action. And it's not just about the internet. This light trap idea is used everywhere. In medicine, doctors use endoscopes with these fibers to see inside a patient's body without doing a big surgery. We see it in those beautiful decorative lamps with glowing fibers. It's truly a fundamental technology for all of our modern communication. Phew, we've covered a lot of ground today. We've learned the basic rules of how light behaves when it meets the world. So now let's put it all together into a simple, handy toolkit that you can use for a quick revision just before your exam. This one table summarizes everything for you. For reflection, the simple rule is light bounces, and the key formula is angle I equals angle R. For refraction, the simple rule is light bends, and the key formula is Snell's law. And for total internal reflection, the simple rule is light is trapped, and the condition is that it must go from denser to rarer, and I must be greater than I critical. Go on, take a screenshot of this. It's your perfect last-minute revision note.
So today we've seen that by following just a few simple rules, light can do amazing things. It can create illusions like the bent pencil, it can power our internet, and it can even help doctors save lives. It really makes you wonder, doesn't it? What other secrets of the universe, from the biggest stars in the sky to the tiniest atoms, can these simple rules of light help us unlock? Think about that. We'll explore more in our next session.